we're going to look at the properties of a soap film. And this is a soap film. Look at that. Look how stretchy it is. Actually, maybe soap film is the wrong word because it's really a water film, but the water, of course, has to have soap in it. And there's a reason for that. Water molecules really pull together very strongly, and that creates something called surface tension. And with just pure water, the surface tension is just too much, and so it would break the film. Let's just have a look at the soap film structure. So here we have, here we have a cross section of a water film, and it consists of water molecules. There they are, and those water molecules have different charges at each end. They're polar, so they pull together very strongly, and they pull together so strongly they would break the soap film. So what we're going to do is put some soap in here, and the soap molecule, they don't really look exactly like that, but this is effectively what they do. The soap molecule has one end that likes water, the other end doesn't like water. Hydrophilic, hydrophobic. And they get between the water molecules and keep them from being able to attract each other so strongly and therefore destroy our soap film. Now, one end of the soap molecule is hydrophobic. Actually, it's greasy. And if we make two soap films and try to make them come together, like this, they actually will resist each other because we have the greasy part. The greasy part is resisting the greasy part. And so we can actually play ping pong with a soap bubble like that. And we could go on for quite a while, but I'm going to just break my ping pong paddle, and there we go. So, because of the stretchy nature of the soap film, we can have a look at what are called minimal surface areas. And what I'm going to do here is just play around with a soap bubble. Like that. I'm going to take another ring like this and make sure it's wet because else it'll break the bubble. I'm going to attach it like that. And you can, each of these is a minimum surface area. So you can go like this, you can almost do that. Look at that. There we go like that. You can flip it upside down, bring it across the bottom, bring it back down like that. Okay. All of these are minimum surface areas. Notice here we have a cylinder. We're going to look at that a little bit later. But here's a cylinder, and the ends are spherical. So I'm going to put a bubble on here. Here we go. Like this. There we go. And remember, we're talking about a stretchy surface that's always trying to be as small as possible. And what we can do here is we can make this longer and longer and longer. And in another lecture, we're going to talk about the pressure inside these bubbles. Because when we make this into a cylinder, it's interesting that the radius of the cylinder is exactly half the radius of the cap, or this spherical cap. If I bring them very close together, we get a really interesting minimum surface area. Like that. And I'm going to pull this, break that right there, and I'm going to pull this apart, and if you look very carefully, you'll see there's a very interesting curve there. Now this is hollow, right there, and it's curved like this, and that curve has the same shape because it's purely a tension structure. It has the same shape as a hanging chain. So that curve there to the side of course this is horizontal, has the same shape as a hanging chain. It's called a catenary, and in Italian or Latin, catena means chain. So as the last thing, we're going to look at one really neat minimum surface. I'm going to take this cube and dip it in here into soap, and what happens is we will get the solution to a film that joins all the corners of this cube. There you are. Now notice it forms a little square in the middle like that. If these corners were, say, houses, and we wanted to make a sidewalk which was the shortest walking distance or the cheapest sidewalk to make that would go between all the houses, we could use this as our design. I'm going to dip this once more, and now we get this beautiful cube or a cubic soap bubble, the cube inside. So that's just a little bit about soap bubbles and how they produce minimum surface areas. Try it yourself, have fun.